Watch what happens when a highly volatile, corrosive gas reacts. Compare that explosive energy to this, a perfectly stable, inert crystalline solid. Despite behaving like opposites, these materials belong to the exact same chemical family, group 17 on the periodic table, the halogens. This column spans from fluorine, the most reactive element known, all the way down to Tennessine, a super-heavy synthetic atom pushed to the absolute edge of existence. The diversity across these elements, how they form gases, liquids, and solids, is dictated by a single shared subatomic signature. Every halogen shares the ns2-np5 valence configuration, exactly 7 electrons in their outermost shell, leaving one distinct vacancy. This empty slot prevents a stable noble gas configuration, creating an aggressive thermodynamic drive to forcefully acquire an electron from any available source. Every role these elements play in chemistry, medicine, and engineering is strictly downstream of this shared ns2-np5 atomic architecture. Starting at the top of the column, we find element 9, fluorine. Fluorine's small atomic radius and high effective nuclear charge tightly compact its electron cloud, exerting a massive inward pull on nearby electrons, called electronegativity. Because the positive nucleus is so close to the outer shell, this intense pull makes fluorine aggressively reactive. Once fluorine captures that missing electron, it refuses to let go. It forms robust, stable structures, like the unbreakable carbon-fluorine bonds used to synthesize advanced modern materials. This bonding property also integrates directly into our biology. Fluorine binds with dental enamel to form protective fluorapatite, shielding teeth from decay. Stepping down one row, we reach chlorine, element 17. Chlorine adds a 3p electron shell. This extra layer increases the atomic radius and slightly shields the pull of the nucleus, marginally dampening the extreme electronegativity we see in fluorine. This slight reduction in reactivity allows chlorine to act as a controlled oxidizer. It strips electrons from pathogen cell walls, effectively neutralizing them without destroying the surrounding medium. This oxidative capacity is applied on a massive scale to disinfect millions of gallons of public drinking water and keep municipal pools clean and safe. At the top of group 17, small atomic radii weaponize the ns2-np5 configuration, creating gaseous elements defined by their oxidative power. As we move further down, group 17 presents a macroscopic anomaly. It is the only periodic group to span gas, liquid, and solid states at room temperature. Drop down to element 35, bromine. It is the only nonmetal on the periodic table that exists as a liquid at room temperature. This phase change is driven by a structural shift. The addition of the 4p shell massively increases electron shielding and the overall volume of the electron cloud. A larger electron cloud is easily distorted, creating polarizability. Electrons shift to form localized instantaneous dipoles. This distortion generates London dispersion forces, temporary attractions between adjacent bromine molecules. These forces overcome ambient kinetic energy, condensing bromine from a gas into a dense liquid. This heavy, stable liquid state allows bromine to be engineered into flame-resistant materials and specialized medicines. Descending further, we find iodine, element 53. Iodine's massive 5p shell makes its electron cloud so polarizable that the resulting dispersion forces multiply exponentially compared to bromine. These maximized intermolecular forces lock iodine molecules into a highly structured solid crystal lattice at room temperature. Because iodine is less reactive than fluorine or chlorine, it can be safely incorporated into organic molecules. This allows the thyroid to capture iodine from the bloodstream and use its large atomic mass to synthesize hormones that regulate our metabolism. As we descend the group, expanding electron clouds transform aggressive gases into structurally vital, condensed materials. Past iodine, the narrative shifts away from expanding electron shells and directly into an increasingly burdened nucleus. Element 85, astatine, possesses a nucleus so massive and proton-dense that it introduces a structural instability. The strong nuclear force can no longer hold the entire assembly together. This instability results in astatine being the rarest naturally occurring element on Earth, constantly destroying itself through radioactive alpha decay. This exact decay mechanism is currently offering promise for the future of targeted alpha particle cancer therapy. Astatine releases high-energy, short-range radiation that can obliterate malignant cells without damaging the surrounding healthy tissue. Finally, we push to the absolute edge of the periodic table to find Tennessine, element 117. At this extreme mass, we encounter relativistic effects. The immense positive charge of the nucleus forces the innermost electrons to orbit at significant fractions of the speed of light. These relativistic speeds alter the geometry of the entire atom, making Tennessine behave differently than classical halogen models predict. At the very bottom of group 17, the sheer mass of the atom overrides classical electron chemistry, turning halogens into fleeting radiochemical tools. Looking at the complete journey down the group 17 column, from fluorine to Tennessine, a unified system emerges. This dashboard displays the chemical trends governing the halogens. The NS2-NP5 valence shell provides a baseline of reactivity. As the atomic number increases, electronegativity plummets. Conversely, atomic radius and polarizability rise rapidly, driving the precise phase changes from gas to liquid to solid. The macroscopic result is a journey that starts with gaseous oxidizers used to purify water and harden materials. It transitions into heavy liquids and dense solids, essential for flame resistance and biological regulation. And it ends on the frontier of unstable, super-heavy elements used to target tumors and investigate new physical laws. The halogens demonstrate how a predictable subatomic architecture can be leveraged to solve specific challenges across chemistry, medicine, and material science.